Hello and welcome back. I'm sure you enjoyed that little break. How long it might have taken for you to get that energy flow back. Welcome back. I'm now going to show you how you can create those four user tasks and with the help of System Interrupt. So let's go into our IDE. I already opened for easy use. So it's already open. We're going to start as a new project. To do that, you need to go to File, New, STM32 project. So this will allow us to set the target board, which is a Nucleo F411 board. You need to set this up first. Okay, go to board selector and you know which one you're going to target to. So it is Nucleo F411RE. Select that board and then hit next and give a program project name. So we are on day 18. I'm going to implement that as day 18 as task scheduler. This is on the part 1, so I'll write it as that and start from scratch. So I'll target as empty and then finish. So this will create all the necessary files. As you see, the project tree already started. Once it finishes, it will give all the included files. Then we can start programming on that. And we're going to verify the output in form of the printf style debugging, which you learned from previous session that printf needs an ITM send character. So we need to copy from syscall, copy those piece of code from the previous day. Maybe I showed you earlier on day 2. You're going to copy that and paste this into this system call, so you can verify by using printf style debugging. I'll show you from there. So I'll close all the open files already, not to confuse you, and we'll go on to, we are on day 18, task scheduler. I'm going to click source and going to open main.c, and I'm going to delete what's in there already. As you know, backslash star and star backslash, this is for our reference to tell what file name it is, who has written the program, and also tells the other programmers to let them know where this program going to sit, whether is it on the header or will it be on the bottom, on the footer, or will it live in the middle of the program. So for anyone who can come and realize in the real-time scenario, they will know where this program going to connect in their sprint section. And also there is a session to show this is a licensed controller that you're going to use. So let's leave it there. I'll delete all the built-in coding lines to start off with, and we're going to use the printf statement. So therefore you need to include the input output library. So I'll create that library stdio.h, sorry, lowercase o.h, and then you need to go to system call and print that ITM character. We don't need that. I'll delete. So I'll just simply write a simple printf statement for our debugging. So testing debug, the comma. Because we're using printf style debugging, I'll go to the day 2 syscall. We'll copy this syscall program, the small code that I shared. Open syscall, this ITM debug exception. So you need to copy this whole ITM character up to here, copy this. Come to today's program, day 18, go to syscall. You got to include this in here. Include it, and then copy this to send character ITM underscore send char. You need to go to write which if you scroll down you will go to right, and in the for loop comment this and pass the function, call the function here, and then pass the variable pointer plus plus, and just save that. I'll close this so I won't get confused. Also close this so I won't get confused. So we did the initial saving of all the files that we needed to run this program. Next, the usual step, as you know, we need to generate the ELF file. To do that, right click on the project name, click on build project. This will start to build up all the necessary ELF format files, the executable link format files, which we need to download to the target board to run the program. 0 errors, 0 warnings is always a good start. And now we need to set up the debug options. Go to program name, project name, right click, and then go to debug as. As you know, there is two different options. Today I'll show you how to select the debug via configurations. This you learned very early, so it comes as here. You need to double click on that, and this will link you to that .elf. Otherwise, you can also directly choose STM32 in the debug option. That will avoid to choose this step, so that's what a difference. Then go to debugger. Always make sure you enable this interface ST-Link. Scroll down for the serial wire viewer, also enable this, and then go apply and then say debug. This will change from C perspective to debug mode perspective, so that's on there. Okay, switch. We are inside the debug mode. Now we'll go and declare all the pointer variables and then define all the macros that we need to use in this program. Let's first start off with initializing the task space. For each and every task, you need to create that private stack and the space, so we will start by doing that. So I'll define some macros first. Define macros. Start off with hash define the size, the 128 kilobyte size we are calculating into 1 kilobyte from that for the stack. So size of the task with 1 kilobyte. Okay, copy this, and now you need to schedule this first task and then size schedule for the task. So just say you can give the full name, doesn't matter, so you won't get confused, and then you're going to link to that task schedule, and then you need to say how many tasks are there in the program right at the start. So we are going to learn about 4 tasks, so the maximum tasks is defining here to be 4. Okay, and the next step is to give the location of the SRAM, the start address and the end address. First we'll go with the SRAM start and then declare all the stack locations. First define SRAM start, SRAM start, and the SRAM start will be where if you get stuck, if you don't know where the SRAM is, if you go to the a linker description on the flash memory, you will get the SRAM start address. So this is the origin, it starts from here. So you got to copy this from the linker description file, go to main program, and you need to say that's where it's going to start from. Use for unsigned, so I'll copy from flash.ld description, and then now you're going to say the SRAM size for the stack. Sorry, I'll copy this, copy, paste. Now is the SRAM size of SRAM, size of SRAM. As you know, it's 128 kilobyte. 128 KB. You're going to link that with allocating that to 1 KB. So this is 1 KB allocation. Okay, so we define the size, then we need to give the end address. We started, we have to end. End will be the start of SRAM start plus the size of RAM, so it will be the next frame is Control V plus the size of SRAM. Size of SRAM will be this, then you close. SRAM end. Okay, so now let's define the stack. So macros for stack space. This is for all the tasks. So first I will define for task 1, and we can just copy that 4 times and use it and just modify it. As define task 1 start stack. Start will be, as you know, the end of the SRAM. End is the start of the task. Copy this. We need to create 4 tasks. So task 2, task 3, task 4. The second task will be the SRAM end plus the size. SRAM end. Need to link that with the task size. Size underscore stack. Sorry, the task. I'll just copy. Size task. Control C. Okay, so likewise, you need to set for the SRAM this and then paste it here. That's for task 2, task 3, task 4. Will be 1, this will be 2, this will be 3, and this will be task 3 and task 4. So now we declared all the stack space macros, which is really good. Now let's go and build the project to see if it's error free. So build, right click, build. Okay, good sign. So now we're going to implement the system clock macros. For system clock, that is 16 megahertz clock. So you got to define the high-speed internal clock. Define HSI clock, which is nothing but 16 megahertz. 16, 2, 3, 4, 5, 6 unsigned. Okay, this is the system clock. And then you need to load the value for, we are generating 1 millisecond that we learned in the system ticks. So for that you need to load that value. So hash define systic load, systic timer clock linking to the high-speed internal clock. Did I put clock? High-speed clock has to be, the label has to be the same, otherwise it will throw errors. So make sure you have written the same. So this is to generate generate for every millisecond, that is 1 millisecond. Okay, that's good. So just to give you a bit of a definition to that, so it will run the handler routine, and it will run in task, the round robin fashion, and it will allocate 1 millisecond for task 1, then it will go to task 2, then it will run for 1 millisecond, and then it will go for task 3, it will run for 1 millisecond, then it will go to task 4, 1 millisecond, then it will go back to task 1 and finish it short. So likewise it will continue allocating the tasks. So we learn from the formula to generate 1 millisecond. That is 1 millisecond is nothing but 0.001 second. You need 16,000 as a clock value. 16,000. This is the counter reload value from previous session. Counter reload value. Okay, so we declared that. Now we need to go to starter file and write the systic handler, as you know. So go to starter file, copy the systic handler, and we're going to look for systic handler. Yeah, copy this and then write a function for the handler. Go to main C. this here, systic handler of void. Okay. And you got to call that in the function. So you need to initialize that init systic underscore timer of. I'll fix the label in a minute. I'm just writing the steps. Tick hertz. Init systic. So you got to write this program shortly now. So HSI tick hertz and init systic timer, stick underscore timer. Okay, and then started the handler, which is good. So now let's write for the systic we defined. So we're going to enable the declare pointer variables. Declare pointer variables. Okay, the first one, you need to do the tick hertz underscore t. Tick underscore hertz. And you're going to run for 1 kilohertz, that's the 1 millisecond tick. Uint syntax error. Uint of 32 underscore system error. Syntax tick, or has it to be? I'll check this one sec. I'll declare all the rest. Then you're going to call the init system timer. So this init system timer, you need to call that program. So void init underscore sys timer systic tick timer, passing the value of uint 32 underscore t of tick underscore hertz, tick underscore hertz. So generate uint tick uint 32 tick underscore 1000, passing that value, this value, into the function. So copy this and write this function now. Control V. Okay, so inside the system tick, you don't have to do anything. 1 millisecond we have written. So right click for function to see what error that is. Right click, build a project. 3 errors with 0 warnings. So what are those errors? Undeclared, undeclared, init system timer, init system timer tick underscore horizontal. Uint 32. Please go and have that break. When you come back, I'll finish the rest. It's not long to go. We're going to write the sysdig timer program, and then we're going to copy all the fault and leave it here for generation. So I'll give you a short break. Once you come back, I will show you how to write this init sysdig timer. I'll see you back shortly. See you then.